flavor models. So that's what.
Thank you very much, and welcome. Good morning, everybody. To the third lecture. So in the first lecture, we talked about neutrino mass mechanisms, based on the one basic ones. In the second lecture, we talked about something unified theories. And in the third one, we'd like to talk about flavor puzzle, the neutrinos mechanics for flavor puzzle, and how one can with models towards understanding where the flavor structure comes from. Oh, yeah. Did somebody not understand what I was saying up to now? Or was this clear? So, even without the microphone, could you understand me before? Or should I repeat what I just said? No. Okay. So, I'm going to talk about neutrinos and flavor models. And the plan in flavor model building is to try to understand where the flavor structure comes from. So basically this flavor information that I showed you on the first day, so the masses of the fermions, the mixings of the fermions. So that's the idea behind flavor model building. And it's very important to go beyond this, namely to derive some predictions that we could test in future experiments. Because this is the only way to find out if the ideas that we are developing are on the right track, or if we are going in the wrong direction. So we need to have the interaction with the experiments and the feedback from the experiments that could falsify our models and tell us where we should not go. Okay, so the flavor puzzle in a sense has various aspects, and here basically four of them. One aspect we may call the standard model flavor puzzle. So this is the question where this hierarchy between the quark and lepton masses comes from, for example. So that's what we also already have without the neutrino masses. The neutrino masses are of course adding certain new aspects to the flavor puzzle. So we have the small masses of the neutrinos, which is also flavor information that we get. And as I've already shown you, we have large mixing in the neutrino sector, which is very different from the quark sector. In the quark sector we have a small mixing, in the neutrino sector we have a large mixing. So the flavor puzzle gets a lot more bigger when we include also the neutrino data. So then the next thing is that we already talked yesterday, when you want to go to grand unified theories to theories in very high scales, we would like to extend the theory at a TV scale maybe with some supersymmetry extension or a different kind of extension in order to solve the gauge hierarchy problem. So this means we introduce new particles, and these new particles can also come as a flavor structure. And that's kind of the new physics flavor puzzle. So I'm not going to speak much about the new physics flavor puzzle, for instance, the flavor structure of a supersymmetric extension here in this talk, but that's even another aspect of the flavor puzzle. And then finally, the third one, which I put a bit separately here, it also exists within the standard model, is the puzzle of CP violation. So we have within the standard model the so-called strong CP problem, which I discussed with some of you after my first lecture. So that's the problem in the standard model. I didn't write this down actually in my first lecture. There's also an FF dual term, which is CP violated, which is strongly constrained by experiments. So the question is why this term is not really there, or why this has kind of some suppressed coefficient. And this is the so-called strong CP problem. There's another puzzle which I find interesting, is that when you look at quark unitarity triangle, then you find that there's one angle which is almost 90 degrees. So this is angle alpha of the quark unitarity triangle. One may also ask if this is telling us something, or if this is just a coincidence. So this is not so standard to think about this, so let me expand a bit more on this alpha equal 90 degrees. Also, and it comes about when you look at the model. So this here is the general unitarity relation for the CKM matrix. You get various relations. So the diagonal ones for I to j is 1. If I is different from j, it should be 0. And if you look at one of the relations, so actually the ED relation here, then you get this combination of elements must be 0. So you can put these complex numbers here together as sides of such a triangle. And then you find that these numbers end up zeros on the complex plane this triangle closes. That's used to test also There's a key violation in the quark sector if the Standard picture is correct. So if such a triangle is not closing, this means there must be new physics, so that's normally used for such a test. But if you look at these angles here, this is practically the P phase that I've already shown you, but this alpha angle here, the experiment tells us that this is quite close to 90 degrees, so almost a right-angled unitarity triangle, which is, yeah, it could be purely an accident, or maybe it's also telling us something. This year's data from 2011, I also put some better data from winter 2013, last year. So it has changed a bit, but it's still, it always kind of circles around 90 degrees. So that's, I find it really interesting observation, and I will come back to the question if this is maybe telling us something about the origin of the P evaluation a bit later. Okay, let me start about some general considerations. So when people were thinking, okay, how can we understand in the flavor structure, what you're doing is, okay, you're writing down the mass matrices, or the things that we know about the mass matrices on a certain basis, maybe, for the up quark, down quark, charged lepton, maybe also the neutrino mass matrix. There we know much less, so we have no idea about the mass scale, for instance. Then you kind of look at it and you say, okay, can I see some structure, or is there any organizing principle? If you look at these matrices, it's not so easy to really see what's going on, because in fact, you can have very different structures of the mass matrices. And already a long time ago, this was classified as basically three possibilities that one can think of. So the first one is called kind of anarchy in the mass matrices. So this means there may be some kind of random Bayesian flow, and that's just determining just by accident values of the mass matrix. And then you can see if you have some good random number generator, maybe you can find the right answer. It's completely random. And this is something which in the quark sector maybe does not work so well, but for the neutrinos, because we have lots of large mixing angles, it could very well be that this is just purely random. Yeah. And people are still considering this, but I think you cannot really make any predictions when you say it's just random. So it's just kind of giving up on the way of explaining this, but it's still a logical possibility. The other thing that people have tried is that one can say that, okay, all the numbers that are there, if they come from renormalizable operators, they should not be very much suppressed. They should all be kind of order one. Yeah? And indeed, if you have right ideas of numbers, order one, you can also, with a bit tuning, get some hierarchical eigenvalues even. And this is kind of the way to require some democracy here in the mass matrices. So this means all elements have the same rights, or the same order. Okay, and the third possibility is that you assume some kind of hierarchy in the mass matrix, which means the third element is the biggest one, like order one. Then you have here elements which are smaller, and then these elements here are very much smaller. And sometimes, if you look at the quark sector, some hierarchical structure is what is actually, I think, suggested by the data. So you have a strong hierarchy, and even if you can do this also with a democracy here, so you have to find a small determinant despite the fact that you have large entries here, or just by some random number generator. So the quark sector suggests that you have some kind of hierarchy out there. So then, for example, so the down quark mass matrix can look, from the structure, it may look like this here. So here is the largest element, quantum quark mass. So it's not really order one, but it's the largest. Then here, these elements are smaller and the order of the strange quark mass. Or here, it's like the bottom quark mass, like the 2-3 mixing angle. So it's kind of suppressed by this small mixing. And here, the bottom quark mass, like theta 1-3. So that's also kind of easy. When you have a mass matrix which is hierarchical like this, you can also read off just the mixing angles, the left mixing angles, by taking here this element divided by the third element, or the 3 element divided by the 3-3 element. This just gives you kind of the mixing angles. So in a hierarchical matrix, you can just read this off in a small mixing approximation just like this. Okay, now let's get a bit into more details, and first start with the quark sector. So in my lecture, I don't want to specialize in neutrinos. I would like to also include quarks in the picture, because as we've seen yesterday, there may also be some relation between the flavor in the quark and in the lepton sector. Okay, so the first thing I would like to discuss, and what people have also found very interesting in the quark sector, is the so-called TST relation. So it comes about when you look at the 1-2 block now of the mass matrices in the quark sector. And for instance, if you start with the down quark sector, and you make a very simple assumption, which is that the 1-1 position here of this mass matrix has a 0 or very, very small entry. So if I write a 0 here, it doesn't have to be an exact 0, it can be something which is just much smaller than this 1, 2 to 1 and 2 entries. And you may also just assume that this matrix is symmetric. So you see yesterday, if you use some kind of standard Higgs embeddings, then these matrices from Gauss turn out to be symmetric. And this 0 or 1 element or the small 1 element can come about if you have some symmetry which is not allowing something to stand there at the same operating order than the other entries. So something that can easily come out of the model when you have extra symmetry. So what's happening then? So you have, so you can read off your mixing angle, your 1-2 mixing angle, just this element over this here. So that's theta 1, 2, sine theta 1, 2. In small mixing angles, you can just write theta 1, 2. And we have the eigenvalues. So the biggest one is approximately just y. And the smallest eigenvalue, so you can use the same formula then for the Caesar mechanism actually, when you have small entries here, it's just y squared, it's just x squared over y. So you have two parameters, you can calculate 3 values out of this. You find that then the 1-2 mixing angle, for instance, you can say is predicted from the masses of the strange quark and the down quark, which is measured. So it's the square root of MD, so it's the square root of MD over NS, and that turns out to be about 30 degrees, which is just the Cabibbo angle that is there in the CKM matrix. So the 1-2 mixing angle in the CKM matrix. So at least it's very close. So this gives you a relation between this kind of down mixing, or it gives you some kind of understanding why we have a mixing of this order in the CKM matrix. So you can play the same game for the up quark mass matrix as well. So again, with some different parameters, x prime and y prime, and you find that the 1-2 up mass matrix mixing angle. So you have also diagonalization matrix, left diagonalization matrix in the up quark sector is now square root of mu over mc, and turns out to be about 2.6 degrees. So can we learn from this? First of all, of course, the total CKM mixing is not only coming from the down sector, so it's here in this general basis coming from both sectors, from the up and the down sector. But if you have a larger hierarchy, this normally means that you have a smaller mixing. So it's quite typical that the mixing mainly comes from the down quark sector, where the hierarchy is smaller, and in the up quark sector, there's a bit smaller mixing because the hierarchy is much larger. And in this sense, also, this here is not an exact statement, but one can say that quite typically from these considerations, it may come out that the mixing comes dominantly from the down quark sector. So that's kind of one thing which works quite nicely in the quark sector. Okay, there's another thing which now comes to this possible origin of this alpha equal 90 degrees, which I've mentioned just at the beginning. So if you ask how could this come about, there's a quite interesting possibility when you now consider, again, hierarchical up and down quark mass matrices, where you now have zeros in the, or a 0 in the 1-3 element. So that this 1-3 up and 1-3 down mixing angles are 0. And when you require this, then this gives you a few interesting relations, which are also working quite nicely. And so the first thing is that we get a prediction for both 1-2 mixings in the up and in the down sector. This is basically just that you're changing your parameterization. So you you don't have a 1-3 mixing anymore, but you're generating this 1-3 mixing out of the 1-2 mixing in the half quark sector. So you're predicting here that the 1-2 up is about 5 degrees, and the 1-2 down mixing is about 12 degrees. So that's again close to the Cabrillo angle, which goes nicely. And we get something else. Namely, that this angle alpha of the quark unitarity triangle is now given by the difference of these phases for the complex 1-2 up, 1-2 down, and 1-2 up rotations. So the difference in these phases is, so you can think about this as complex 1-2 rotations, which come as a phase. This difference is really just this angle alpha in the quark unitarity triangle. So this means what you can do is you can explain this alpha equal 90 degrees easily, where you have, for instance, 90 degree here in the down sector, 0 in the up sector, or 0 in the down sector, minus 90 degrees here in the up sector. Such a phase of 90 degrees just means that the corresponding elements are purely imaginary, whereas the other elements are purely real. So you can also explain CP violation nicely, and this basically, so when you have this alpha equal 90 degrees, then this means that you're not exactly predicting the right dual CP phase in the quark sector. So you basically have only one independent CP phase here. Alpha equal 90 degrees translates directly to this delta dual CKM equals 70 degrees. So you can explain CP violation in the quark sector very nicely with only purely real, purely imaginary mass matrices, for instance, of such a form. And what exactly you need is given by this phase subgroup. Yes, so this is something which you can put there in addition. Yeah, so it's not. So the only thing that is required on the still is here and there. But you can even combine this with the zero there, and then you basically both features. So that's very well possible. Then you're kind of going one step further, that you're also explaining the size of this 1-2 mixing here by this ratio of the quark masses. So these things all are really necessary to explain this, but I think it's a nice way and a nice simple way to understand exactly where the CP phase in the quark sector is coming from. That could be done by this sort of phase. Okay, the next thing, which is where we've already touched yesterday, is this question where the mass hierarchies are coming from the quark sector, and this goes under the name Fröhlich-Nielsen mechanism. And yes, I mean, as we've seen from the data we discussed yesterday, so we have some quite strong hierarchy in the mass matrices of the quark, so just some kind of ordering principle. And how you could do this is actually the following. You could consider a case like this, that you have the mass from the search family is coming from some renormalizable operator. You kind of like this, it's just a simple term in your Lagrangian, a normal Yukawa coupling the search generation to the left counterpart, the right counterpart to the transversal Higgs field. And then from this you would expect some kind of unsuppressed Yukawa coupling. But for second family, for example, you would like to explain why this Yukawa coupling is smaller than this one here, then you can think of that it may come from an effective operator. So an effective operator has some extra field in here, which gets a maximum expectation value, then it will be suppressed by this maximum expectation value over the mass of this field with this exchange here in order to generate the effective operator. So you're getting some entry here in a position which is smaller, suppressed by this ratio, and this could give you some kind of organizing principle here. But, of course, now we have to think, so why can't I just write down the same homological operator here for the second family? And now we, in order to have a model which is really explaining such a hierarchy, you need to add extra symmetries. which are allowing here this renormalizable operator, but which are not allowing it here. So that this means here you have renormalizable operator plus I operators, but here you start with this effective operator. And this is the Frege-Nielsen idea that you can add some extra symmetries. Like the simplest case would be to add some kind of U1 symmetry, where the fields here, for instance, have the following charges. So we have, and this is just a very simple toy example. So we have for the third family in X with 0 charges. So this means when you go back, this here you can write down. It's completely neutral in your inversion. But then when you look at, we have here for the Q2 and for the second family of the right cardinal down form, you have different Frege-Nielsen U1 symmetry charges. So this means combining this with the X is not neutral anymore. So you cannot write down this renormalizable operator in your Lagrangian anymore. So you have to do something. You have to combine it here with this field. Now the charges add up to 0. And this means you can just write down this effective operator. That's allowed by symmetries, whereas the other one is not. And this is exactly how this kind of horizontal symmetries can select where the entries of the Yukawa matrices are generated and by which order of operator or which kind of operator with which fields they get generated. And this now connects to what I was touching yesterday in my lecture about grand unified theories. When you want to explain these mass ratios for the quarks, then you can use exactly this principle. So you've seen you can have here different kind of embeddings of the Standard Model Higgs into web representations. You can also give these fields some charges, such that kind of one embedding can appear here, but a different embedding can appear here. So we have this kind of capital Phi would be a good field to appear here, but the capital Phi prime would be a good field to appear here. So we can do this by giving different charges to the Higgs field coupled to the different elements of the mass matrices. And you can, of course, also combine this then with these kind of SU5 operators, which give these different quark-lepton mass ratios. So this is all nicely compatible with this idea of explaining the hierarchies by the Frege-Nielsen mechanism. Okay. Oh, this is just for this toy example. So in a full theory, you have to very often introduce more of these fields, and I will give later with an example why it's also useful to introduce more, and also why you go beyond this kind of simple U1 symmetry and consider maybe different kind of symmetry. But that's the simplest example. If you think when you have some horizontal symmetry, and now you can also see what is called a horizontal symmetry. So it gives different charges to the different families of the field. So it allows you to distinguish on the different families, and so kind of introduce structure in this kind of horizontal sense between the different generations. Okay, so that's basically about the lessons for the course. Let us now turn to the Laplace section. Okay, and first thing I would like to discuss with you is something which is called sequential dominance, and this allows you to understand a bit kind of how the large mixing can be realized in the Laplace sector when we have some type 1 Caesar mechanism. Because so the matrices that you see in your Lagrangian, this is just some here, then let's put some general neutrino Yukawa matrix as a kind of right-handed mass matrix for the right-handed field, which I've also put in a diagonal form. This is our generality. Okay, so these are the parameters that you have, but kind of how can you see from these parameters what is the mixing in the neutrino sector? So it's not, just looking at this, it's not so straightforward what it is. So you say, okay, yeah, I have to calculate it, I have to calculate the mass matrix, I have to diagonalize it, certain eigenvalues, eigenvectors, and so on. But there's actually a very much simpler way to look at this, which is on the phi generic. So first of all, one thing I would like to say is the following, that here we have diagonalized it, and we call this MA and B and C. And these columns here of the cover matrix, we are using a left-right convention for the cover matrices. These are the couplings of the three leptons of the three neutrinos in left and doublet to the three right-handed neutrinos. So I can name them the right-handed neutrinos with right-handed neutrino A, B, and C, and then these here are the coupling of this first right-handed neutrino to the three Sunderland neutrinos. And then over to B and C, these are the couplings to the second and to the third right-handed neutrinos. But up to now, it's completely general, and when I ask how we have to choose now my A, B, and C vectors here in order to be consistent with the mixing data in the neutrino set. So now this sequential dominance is the following idea that you say that, okay, now when I look at the neutrino mass matrix, I have these three contributions which come from the right-handed neutrino A, from the right-handed neutrino B, and from the right-handed neutrino C. And these contributions can be calculated by having here this column vector transpose, so this A transpose, over the mass of the right-handed neutrino A, and the same for the B and for the C. So this is basically just splitting this up into these three contributions. And if we have situations in the cover matrices are kind of hierarchical, also that the masses of the right-handed neutrinos have some kind of hierarchical values, then it's quite likely that also here we will have some kind of hierarchy between these different contributions. So, one is the biggest one is a little bit smaller, or somewhat smaller, and then the third one is much smaller. So that in this sense you have kind of some organizing principles between these three conditions. And if this condition is satisfied, then you have the conditions for so-called sequential dominance. So this will kind of automatically also give you a hierarchical neutrino spectrum. So this is not absolutely necessary. So you can have situations where this is not satisfied, but it makes it quite easy if these conditions are given to understand how the large mixing is generated. Because then, from this dominant contribution here, you will get the mass of the heaviest of the light neutrinos, so the M3 for the normal hierarchical spectrum. And you will also get this mixing at 2 speed, just from this contribution dominantly. And the subdominant contribution will give you the mass M2 and the mixing angle θ2. And then you have some kind of subdominant contribution which just gives you the mass of the lightest of the light neutrino, but we don't know where this mass actually is. It could be very, very small. And this is kind of a subdominant contribution. And only the mixing angle θ3 may come from interference of these terms. So now if this condition here is satisfied, then there are simple formulae where you can connect the mixing angles in the neutrino sector to these elements of this general Yukawa matrix in the basis of diagonal neutrinos. So, for instance, the mixing angle θ2 3 is very simple. So the tangents of this angle is just the ratio over this A2 and A3 element. So very simple formula. This just means that when you want to have a mixing which is close to maximum, so like 45 degrees θ2 3. So that's what the data is telling us, kind of roughly. And what you need is just that the second and the third element of the coupling vector to the right-handed neutrino A must be approximately equal. Okay, so that's just one condition. You see that in this matrix you need two elements which are approximately from the same order. Then also you have here a mixing angle θ1 2, which is given by the ratios of the elements of the second column here of this B column. So they're coupling to the second right-handed neutrino. And I've considered here for simplicity the case that we have real Yukawa matrices. So of course they don't have to be real, but they are complex. And we have here some complex phases which appear, which you can determine by some consistency equations. It's practically the same, but just for simplicity we may consider them as real. Then we have here just the sign of these two elements,